Hi, I'm Ane, this is Rahul, and this is Murad, and our project focuses on improving reforestation through drone technology. Around the world, forests are being lost due to deforestation, wildfires, and land degradation.
Traditional tree planting is often slow, labor intensive, and difficult in remote or dangerous locations. This makes restoring large areas of land both expensive and time consuming.
Our driving question was, how can we design a lightweight, reliable, and efficient system that allows drones to disperse seed balls accurately for large-scale reforestation efforts?
The second part was research and key insights. We started by researching current drone-based reforestation systems and seed ball technology. We found that drones are already being used to distribute seed balls in areas that are difficult for people to access, using the FX UAV technologies.
One important insight was the dispersal mechanism. It is just as important as the drone itself. If seed balls are released inconsistently or become jammed, the efficiency of the whole entire system can decrease.
We also identified several constraints. The mechanism needed to be lightweight so it wouldn't overload the drone, simple enough to manufacture with available tools, and reliable enough to avoid jams, as well as capable enough to hold multiple seed balls at once.
These findings helped us focus on designing a compact seed ball storage and release system rather than modifying the drone itself.
Now, the third thing we came across was ideation and early concepts. To generate ideas, we used not only sketching, but also brainstorming and CAD modeling. We explored several different concepts for storing and releasing said seed balls.
Some of our early designs included gravity-fed tubes, rotating drum, and a hopper-style container, and each design had different advantages and challenges.
After comparing the concepts, we selected a box-based design because it offered the best balance between capacity, simplicity, and reliability.
We also shared our designs with classmates and mentors. Their feedback helped us simplify the mechanism and reduce unnecessary components that could potentially fail during the operation or slow it down.
Our next was prototyping and testing. We moved into prototyping, and we used CAD modeling software such as Fusion to model our designs and 3D print physical prototypes.
Our first prototype successfully held seed balls, but we quickly discovered several issues. The servo motor wasn't mounted correctly, and the clips were also too flimsy and kept on breaking.
Using rapid prototyping with 3D printers and cardboard, we evaluated the design and conducted multiple tests and designs to solve the issues which wreaked our designs.
Based on those results, we modified the design to fit well on DJI drones, and we also went through several design stages to make sure it was adjustable for all types of DJI drones. We initially tested a screw system, where you line up the correct holes and screw the clips to secure them, but due to limitations with the 3D printer, we ultimately decided to use Velcro for the final design, as it was just as strong and much easier.
We also tested using slanted clips based on the angle of the drone wings, but after testing the straight and slanted clips, the slanted clips were much less stable and didn't hook onto the legs as much. For the final design, we increased the height and shortened the distance between the clips, allowing for much tighter and a better fit.
For the electronics, our system went through 3 distinct phases of development. In phase 1, we used the DJI controller itself to trigger the servo motor. This seemed the simplest approach, but we quickly hit a hard limitation. DJI drones don't allow you to control external motors through their native controller, so that idea had to be scrapped entirely. In phase 2, we moved to a more custom solution. We built a system around a Raspberry Pi which hosted a Wi-Fi hotspot and served a simple HTML page. From that page, you could either drop a pin on the map or manually enter GPS coordinates to schedule a drop location. The Pi communicated with a SIM hat through an Arduino, which acted as a sort of bridge between the two. This SIM hat was essential for GPS, and it allowed us to track the real-time position of the drone during flight. But as we looked at this more critically, we realized the Arduino was an unnecessary middleman. It added cost, complexity, and another potential point of failure. This is not ideal for something we'd want to scale and eventually mass produce. So in phase 3, where we currently are, we stripped it back. The Raspberry Pi now directly communicates with the SIM hat, cutting out the Arduino entirely. We also moved away from the HTML page and replaced it with a SIM-based control, meaning the operator can simply send a text message to configure the system and schedule drop coordinates. This makes the whole setup more centralized, more reliable, and more simpler to drop on the field. Throughout the process, failure became one of our most valuable learning tools. Every issue we encountered helped us identify weaknesses and improve the next iteration, allowing us to make the final product much, much better.
Our final solution and potential impact. Our final prototype is a drone-mounted seed ball dispersal box designed to store and release seed balls efficiently during flight.
Compared to our earlier versions, the final design is lighter, more reliable, and less prone to jamming. It also provides more controlled seed ball dispersal.
If developed further, this technology could support reforestation projects by helping organizations restore forests faster and much more efficiently, especially in difficult to access environments.
This project connects directly to STEM's themes such as sustainability, engineering, design, environmental restoration, and innovation. It demonstrates how technology can be used to address real-world environmental challenges.
Reflection and next steps. One of the biggest lessons that we had to learn through this project was that engineering is an iterative process. Rarely does the first design work perfectly.
Throughout the project, we improved our skills in CAD design, prototyping, testing, problem solving, and teamwork.
If we had more time, we would integrate the system with a functioning drone using SMS messaging to amplify the design and collect data on dispersal accuracy and efficiency based on real-world testing.
In addition to our drone seed ball dispersal system, we also worked on a smart walking stick designed to improve mobility and safety for those who are visually impaired among our community, and those people who have limited vision.
The goal of this project was to create a walking aid that does more than provide physical support. We explored how sensors and electronic systems could help users detect obstacles and navigate their environment more safely and independently.
Throughout the design process, we researched existing assistive technologies, developed early concepts, and considered how features such as obstacle detection, user feedback systems, and ergonomic design could improve the user experience.
This project allowed us to apply our engineering principles to a real-world accessibility challenge, where focusing on user-centered design and practical problem solving solved everything.
Thank
you for watching.